Okay, now everything should be working properly. So, I will just move so I'm a little closer to the telescope controls. And there we go. That's the moon. It's a little overexposed at the moment. I'm just trying to get all my windows open so I can see the chat and simultaneously see the moon. Because it's tricky to try doing this with the delayed, like 5 seconds delayed video that YouTube gives. So here I can just turn down the exposure a bit to get more of the moon visible. Okay, there we go. So, right now the moon is at its coolest point of its monthly orbit around the Earth. Right now it is facing, right now it's close to 90 degrees between us and the moon and the sun, which means rather than it being completely illuminated, like front lit like it is during a full moon, it's only half illuminated, which means you get all these interesting shadows here because from the point of view of this camera, the sun is below the horizon down and to the left. So it's lit from the lower left, and you get all those shadows there. So I guess I'll start by commenting a link to this stream on the previous attempt of stream, because I think there's one that doesn't have instructions on where the actual stream is. Oh, and comments are turned off. Okay, well then I will start by talking about what we can see here with this zoomed out view of the moon. It's not all the way zoomed out. You can't quite see the bottom part, but the bottom part is entirely lit from above by the sun down here. So even if I turn down the exposure to make it less, yeah, so I can turn down the exposure like that, and you can still see stuff there, but you can't see any shadows. All you can see are the darker areas of dark rock and a few really bright areas of recent impacts, but you can't see the topography nearly as well, and the topography is always the coolest part. So then if I go back to the more interesting areas, the moon, most of the moon formed a very long time ago, close to the beginning of the solar system's history. So there was a period known as the late heavy bombardment where there were a much larger number of errant asteroids and comets in the solar system than there are currently. And there are less now because they all hit things. And a lot of that happened in a very rapid period about 4 billion years ago. So most of the impacts on the moon are from then. The biggest impacts occurred right at the beginning of the moon's geological history, when it was still active and had molten volume in it. So those huge impacts are all these big dark circles called the maria, or seas in Latin, which then filled with a darker basalt which is why they appear dark. So those are what you can see if you actually look up at the moon. You can see the big dark regions, which are old lava filling enormous craters. And then in the time since, the moon has continued to be struck by meteorites, as has the Earth. But the moon doesn't have any atmosphere or oceans to wear away those craters, so they last a lot longer. So we have, I guess, still pretty far from Ottawa, but up in northeastern, or I guess central Quebec, there's a very large meteor crater, Manicouagan Island. It's a lake with a central island, and it's very visible as a crater, but it's mostly worn down. It doesn't have big walls. It's just a circular lake, and that's because of all the erosion we have here. And a lot of these craters on the moon, especially at the South Pole, are similarly old or even younger, but they last a lot longer because there's no erosion whatsoever going on up there. So this crater right here, a bit below center, is one of the more spectacular features on the moon. Its name is Tycho. I think that's how it's pronounced. It's named after a Danish, I think, astronomer from several hundred years ago. But it's very big and bright. The rock is still all roughed up there. And you can also see that this impact launched what's called ejecta, like debris just from the force of the impact all across the moon's surface. And that's all these lines that you can see radiating out from it. There are other craters that have ejecta. For example, this one up here, Copernicus, you can see a web of lines coming out from it. But with Tycho, you can see they go all the way. You can see a line goes all the way out to here. And those are actually almost, like, they're visible with quite a bit of effort to the naked eye. But of course, much more visible with a telescope. Even with binoculars, you can see them. So, I think now I'll zoom in a bit more. Right now, my camera is binning, so it's considering each square of 4 pixels as a single pixel. But if I turn that off, and then turn up the exposure to compensate, and the frame rate, okay, so there we've got a much more high resolution view. And I guess I'll head over to the South Pole to begin with, because it is the most interesting at high resolution. So yeah, this is the southern end of the moon. If you look outside right now, this is at the bottom, because we are in the northern hemisphere. If we were in the southern hemisphere of Earth, the moon would be upside down. But we're not, so north is up, as is convenient. Here, this is Tycho, the brightest crater that you can see. And you can also now see that it has a mountain, like a little bright point in its center. And that's a common feature of craters. You can see one up here at the upper left, 2 in this crater and this crater. And those are essentially, when you drop something in water, it splashes a ripple outwards, and then the ripple also rebounds towards the center and makes a little peak in the middle. And that's pretty much what happened here. It just solidified while the peak was there. So you get a mountain in the center. There's also some pretty cool stuff right at the South Pole. So if you know, on Earth, the sun never comes very high above the horizon in the polar regions. And on the moon, it's the same. And the moon also has craters, which the Earth doesn't have many of, that are huge and bowl-shaped. So some of these craters here along the edge, where south is kind of like down right in the video, some of those craters on the edge, they're deep enough that the sun never makes it into the bottom. And using spectroscopy, satellites that we've put in orbit around the moon have been able to determine that there's a substantial amount of water ice down there. So those craters are of interest for potentially for landing people, because there would be an easy source of water. They're of potential interest for landing telescopes on the moon, because they're on the ground, which is more convenient than being in space. Because you can point yourself just like the same way I point my telescope, rather than having to steer with thrusters as you would in space. And of course, it's always dark there. There's nowhere on Earth where it's always dark. But anyway, we get the same. We don't need our craters for this video to be always in darkness. We just need them to be slightly in darkness. So you can see along here, where the shadows really stand out, that there's a lot more detail. You can see this long crater here, and these ones right along the edge a lot better than you can see even the ones maybe 1,000 kilometers further in on the left side of the screen. And I may actually try later to take a time lapse of this region for an hour or so as the sun moves across it, because the sun is rising there right now as the moon very slowly turns. And I'm curious to see if it's fast enough to get a video of the light creeping across those mountains and ridges. But the reason the moon turns so slowly is when you have two objects mutually orbiting. Like, the moon mostly orbits the Earth, but that's just because the Earth is much bigger than the moon. When you have two objects in orbit, they will experience a torque that tends to make them stop spinning relative to each other. And because the moon is much smaller than the Earth, it has already stopped spinning relative to the Earth because of that. So every time the moon orbits around the Earth, it spins around its axis once, like it has one day. And because they're synchronized, there's always one side of the moon that is facing the Earth. So we always see the same side, and we just see the sun creep across it over the course of the month. So this crater a few weeks ago would have been very highlighted by the shadows. It's the one I mentioned earlier. It's called Copernicus. It's a fairly deep crater. I'm just going to try to I'll see if I can get any more focus out of this. Yeah, so it's a very deep crater. It stands out very well because it's in the middle of a much darker area. And also it has all these mountains right against it. This mountain range here in a bit below center is named the Apennines, after the mountains in Italy. And it contains some of the highest mountains on the moon. It also contains the landing site of the Apollo 18 mission, which was right around here. I think it was in between these two bright areas, which are mountain peaks. And I'm not sure which is which, but I have taken a picture like this before and then gone and looked at Apollo 17. Sorry, there was no Apollo 18. Apollo 17 pictures, and matched up like the features in my pictures with the features in their pictures, which was pretty cool. We can also look at the first landing. The Apollo 11 guys landed right about here. There's no real common features you can see for them. Apollo 18 landed beside some very big geological features, some big mountains, and a collapsed lava tube where liquid lava flows under solidified lava and then drains out, and you get a huge tube that then collapses. But Apollo 11 landed right here in the middle of a fairly flat plain, which is what you want for an experimental mission. You want to land in a big flat area, because landing on the side of a mountain can be bad. But because of that, they landed amongst a bunch of very small craters that are too small to be seen here. So you could probably identify some of these features against video that they took while they were on the descent, but none of the actual craters that they saw while they were landed are big enough to see from Earth. So let's see. I guess I'll just pan around a little, see what else is interesting. So as you can see, all of those, all of the bright spots, those are craters and crater rims, and that's just because when you have an impact, it roughs up the rock and exposes new rock, which makes it just more reflective. The same thing happens with rocks on Earth. Often a scratch will appear brighter than the weathered surface. And even though there's no erosion up there, there's still a bit of weathering from cosmic radiation and solar wind, which isn't quite the same thing. So here's back where we started. Let's see how much detail we can get right on the edge between night and day. It overexposes the rest of it, but yeah, that's still pretty visible. Well, maybe I'll try a time lapse of this area here. That's got some nice topography. Well, at this point, we've seen the whole moon. I can keep panning around. I may look up a map of the Apollo landing sites and just go through all of them. But this stream will be shorter than the ones last fall because there's none of the great planets are up at the moment. Mars is far away. It was very close to us last fall, and now it's further. And Jupiter and Saturn won't be up until end of the summer. So it is just the moon for tonight, but I will keep going back and forth across it. I am going to look up a location of the Apollo landing sites, and I'll go through and point those out. And if anyone does have questions, go ahead and ask in the chat. When there's no pandemic and these events are in person, that's half of the event. Okay, I've got my map. So, just going to minimize the stream window. I'll be answering any questions for a minute. So, as I pointed out earlier, Apollo 11 landed right about here, on the edge of this Maria, this lava-filled crater. And then oh, I did mix things up. Apollo 17 isn't the one I was pointing at before. Apollo 17 landed right about here. So that was the final mission to the moon, the last people who have stood on it at the end of 1972 were right about here. The one I pointed out earlier landed here, and that was Apollo 15, the year earlier. Apollo 16 landed not too far from Apollo 11, but I'll have to pan the telescope over a little. Apollo 16, it's hard to tell exactly because it's hard to follow maps of these dark areas that have not much except craters, but I think Apollo 16 landed right about here. And then finally, just need to orient myself because the map is flipped relative to the view. But Apollo 12, the second mission, landed here. And the one after it was Apollo 13. It didn't make it to the surface. They had to abort and come back. But Apollo 14 landed just beside 12 right here. And then this map has a number of other landers, but none of them were manned, and there's too many to go through and point them all out. But I guess I can say, oh, actually, no, I was going to point out the first ever moon landing, which was done by an unmanned Russian probe, but it landed in the dark area that we can't see right now. That was Luna 9, and it landed somewhere in here, where it's currently nighttime. Tomorrow night that would be visible, but of course you can't see anything of the spacecraft because it's a meter across and 400,000 kilometers away. Okay, so I'm just now going back to the chat window. Look at the questions. Okay, so crater depth. I don't know all of them. There's a lot of them, and it's kind of hard to tell with the effect of the shadow making some of them seem deeper than they are just because of how they're illuminated. But I do know that, these mountains, they're a crater edge. So this big area here is a crater that's filled in with lava, and these mountains are about 4 kilometers tall, I think, at their tallest. I can look that up quickly, get an exact figure. The tallest one is, I think, Mount Huygens or Huygens. Um, I'll point out exactly which one it is. I'll try to find a relatively zoomed out map so I can find it. Okay, this map's too zoomed. The map on Wikipedia is too zoomed in to tell exactly where, but it's somewhere in here, and it's 5.5 kilometers tall. The more recognizable craters that are more recent and not filled in with lava, such as Copernicus here. Copernicus is one of the larger craters on the moon, and it's about 100 kilometers across, and I think 1 kilometer deep. And the reason I know that is to create a demonstration of how, as I said, up here you can see all the shadows and it looks interesting. Down here you can't see any shadows, so you can't see topography. I 3D printed a scale model of Copernicus crater that's about 15 centimeters across, and I have it in the observatory at Carleton right now, which is not where I am. I'm in my driveway. But in doing so, yes, I learned it's about 1 kilometer deep. Most of the craters are quite a bit smaller. The small ones are more like, I don't know, tens of meters deep. Okay, second question, Sea of Tranquility. As I said, the dark areas are called Maria for seas in Latin because they look like seas, except gray. So the Sea of Tranquility is just one of those, and I will just Google which one in particular it is because I can never remember. Oh, it's the one that Apollo 11 landed in. Sea of Tranquility is this one right here in the center. More usually called Mare Tranquillitatis because, I don't know, science names things in Latin often. But yeah, it's this roughly circular dark region here. And again, right by this bright spot is where Neil Armstrong and Buzz Aldrin landed. Okay, next question. How long does it take to fall into the deepest crater? Well, that would be... I need to do some math, but I know the relevant values, so this will only take 10 seconds in Wolfram Alpha, because Wolfram Alpha knows everything. If any of you are from the coming from the lab class at Carleton, Wolfram Alpha is a useful thing to know. So if the depth is 1 kilometer, well, just falling 1 kilometer on the moon, I did this math wrong. Oh no, I didn't do the math wrong. I just I said M and it didn't know I meant meters. Okay, so falling 1 kilometer on the moon Yeah, maybe. Maybe Jared has done the calculation while I have been trying to do it with a clever tool. That is taking longer than it should. But yeah, I think he's right, about 35 seconds. Yeah, 35.1 seconds to fall 1 kilometer from, you did a running jump down the crater rim. And in that time, you would accelerate up to about 60 meters per second, I believe. Which isn't that fast, but is still faster than the human body can deal with. Because the moon's gravity is, I think, only about 1/5 of the Earth's gravity. Okay, so someone's asking about the resolution on this image. The resolution is, well, the telescope's currently operating at a focal length of 550 millimeters, and the pixels on the camera are 2.2 microns across. They're smaller than you'd get on a usual digital camera because this is designed for planetary photography, which means you're pointing at bright objects that you want to see in high detail. So the resolution is just the quotient of those two numbers. And then if I multiply that by the distance to the moon, I get the distance resolution. So each pixel in this video is 1.4 kilometers, or 1.5 kilometers. Yeah, so this crater, it's about 100 pixels across maybe, and it's about 100 kilometers across as well. And that is, for example, why you can't see the lunar landers even in a Hubble picture. The Hubble's resolution is, well, the Hubble's 2.5 meters across. My telescope is 10 centimeters across, so the Hubble is 25 times the diameter of my telescope. And it's just a better telescope, so let's say it has 4 times the resolution, or 40 times the resolution. That means you're only getting down to like 20 meters per pixel. So maybe you can see a single pixel that's a little bit brighter because the lunar lander's there and reflecting sunlight. But you definitely can't get detail. Although there are plenty of telescopes, or not plenty, but several orbiters around the moon with telescopes, and they can take high enough resolution ground imagery to see the landers. Mars has the same thing, for example. When Perseverance landed, they had pictures of all of the various parts of the vehicle that hit the ground, because only the rover soft lands, its sky crane flies away and crashes, the heat shield and the top section fly away and crash. Okay, so next question is about the failed Chinese lunar lander from a few years ago, and I don't remember, but I did hear about it, so I can quickly look that up and probably give a good, concise explanation and point out where it tried to land. My telescope is in the video description. It is a Skywatcher Esprit 100 ED. It's a refractor. It uses lenses. The lenses are 10 centimeters across, and there are currently 3 of them. There is an optional piece that adds 2 more for improved characteristics at the edge of the field of view. But I don't need that right now because I'm not looking wide field. I'm looking at a fairly detailed region of the moon. If I was trying to, if I was using my DSLR to take pictures of nebulas and galaxies and so on, the field of view would be about 5 times wider. So I would need some of those. I would need better resolution at the edge of the field of view, which would mean using that extra piece. Okay, and I may have been misremembering about the Chinese probe. I don't see one having failed. There was one in 2013 and one in 2019 or 18. Okay, so if just the person who had asked about the Chinese lunar lander, you may have the details wrong. I don't see any of those happening in 2016. But the oh no, okay, it stopped working in 2016. So generally it's very hard to build durable space probes because like you can't service them at all. They just have to work for their entire lifespan without any serious problems. And this Chinese lander landed in 2013 and continued to operate through 2016. And in 2015 it became the longest operational rover on, like the most long-lived lunar rover. So it ceased to operate in 2016. And I don't think they know exactly why that was. There's plenty of stuff that can fail. You need your electricity to work. You need the solar panels to potentially point in the right direction. You need your communications to work. Stuff's hard when you can't service stuff. Like that's something they're just talking about now, servicing satellites in low Earth orbit. So far, it's only been done with the Hubble at a enormous cost. Okay, and we'll see if I can find exactly where this Chinese rover landed. It was in embryo. Okay. So once the video catches up with what I'm seeing, the Chinese U2 rover landed right about here. in late 2013. And its successor landed at the beginning of 2019 on the far side of the moon. On the far side of the moon, but at the South Pole, okay, I don't think it's possible to see it from here. So the far side of the moon isn't entirely well defined because the moon does not orbit in a perfect circle. It orbits in a bit of an ellipse, which means that despite it being tidally locked to the Earth, where one side's always facing us, it wobbles a little back and forth over the course of the month, which means that sometimes things which are on the far side of the moon by only, 100 kilometers might be on the near side of the moon by 100 kilometers a week later. But it seems like this lander was all the way on the far side of the moon, probably like directly across from here or so. Okay, so that new question about the James Webb Telescope. So the Webb is only going to be about 2.5 times the size of the Hubble. So its resolution will still be maybe like 10 meters, which still is not useful for looking at anything that we've put on the moon. And then there are also much larger telescopes. The space telescopes like the Hubble and Webb, they're not really they're not the best we have anymore in terms of resolution. Going to space is good for resolution, but it also makes it very hard to build a big telescope. So right now, the biggest telescopes we've been able to put in space have less resolution than the biggest ones on the ground, and that's because on the ground, you're looking through the atmosphere, and as you can see in the video, the atmosphere wobbles a little. It's the same as what you see when you look at hot air above pavement in the summer, except magnified. Right here it's magnified 20 times. Or no, right here it's, I don't know, you can't really give a number for the magnification of a picture. That doesn't make any sense, but right here it's magnified quite a lot. And that's a serious problem for imaging because like right here it'll wobble out of shape and it'll blur a little because it's moving while the camera exposes. And any big telescope takes long exposures probably, so there's even more blurring. And the way that I'm going to deal with that if I take a picture later is I just take a very large number of pictures and assume that their average is correct, and then use software to kind of distort them back to where it thinks or sort of undistort them, try to get rid of any distortion from the atmosphere. And that has the added advantage of you have a huge number of pictures, and then you can average them, and since you're taking the average of a large number of measurements, the results are very precise. So you can sharpen the image with minimal like fake sharpening artifacts coming up. But the way they do it with big telescopes is they use a laser. They point a laser way up in the atmosphere where the telescope's looking, and it is a special wavelength of laser that doesn't really interact with the atmosphere down here, but once it reaches the upper atmosphere, it causes atoms to fluoresce. And that creates like a fake star very high up that is an ideal point for the telescope to look at. And then it'll have a deformable mirror with hundreds or thousands of individually movable mirror segments that try to do that work of distorting the star back to a perfect point to get rid of that distortion and blurring from the atmosphere. And those are able to achieve higher resolution than space telescopes, just because the biggest space telescopes right now are 2.5 meters across. That's what determines the resolution. The biggest ground-based telescopes are 10 meters across. So if they can cut through the atmosphere with clever tricks, then they can get a better resolution. They still do have the problem of light pollution. No matter how far away from the city you go, there's still a little tiny bit left of the main thing is cosmic radiation interacting with the upper atmosphere. Produces what's called the air glow. You can actually see it if you see pictures taken from the International Space Station. It'll look like there's a little like yellow-green shell around the Earth at nighttime. And that's the air glow. That's just cosmic rays interacting with the top of the atmosphere. So ground-based telescopes have to look through that. The Hubble doesn't. So the Hubble can just point at like a dark spot of sky for a month and see galaxies from 12 billion years ago. So if you see a super high resolution picture of a star that actually shows details of the area around, like immediate vicinity of the star, that's probably a ground-based telescope using those adaptive optics to cut through the atmosphere. But if you see a super deep field of the furthest reaches of space, it's the Hubble. Okay, so at this point, I think I've said all the things I can immediately think of. So I'm going to just pan over the surface of the moon again. And if anyone does have any further questions or requests of specific parts to look at, let me know. If not, once I'm done panning over the surface, I am going to shut off the stream because I can't record while streaming, I don't think. The frame rate and video quality gets impacted, and then I'll try to take some pictures. Actually, I can try zooming in further. I'm not sure how good it'll look in the raw video. As I said, I can sharpen if I record a video and then use clever software tricks. But zooming in like this might just make it look more blurry. But it's still worth a try. Yeah, thanks everyone for showing up. Sorry about the delays at the beginning. I'm a bit out of practice. It's been several months since I've done this. Okay, so here it's going to go out of focus, and then I'm going to need to fix the focus and turn up the exposure. Because I just inserted a 2x focal extender into the telescope, which will zoom in by a factor of 2, but also make it blurry and out of focus, and make it darker by a factor of 4, because the light is more spread out. Let's see. There we go. Okay, so that's not bad actually. You can really see the wobble though. Um, it's called it's called atmospheric seeing. The that turbulence in the atmosphere, uh, and it limits the high resolution that you can get on solar system objects, and to a lesser extent, deep sky objects. But you can definitely see more zoomed in like this. So that's Copernicus crater. You can see you can see a bit more topography in the crater rim now, and 3 peaks at the center. Here's back to the Apollo 11 landing site. Still can't see anything other than some very large craters. But if anyone's interested, you could probably take a screenshot of that and then work out exactly where the lander ended up. Or where it still is, because the bottom half, the descent stage, it doesn't take off. Generally with rockets, you drop the parts you're done with. When you're going up, you drop parts off before you reach orbit, because they've run out of fuel and you don't need that many engines anymore. Landing on the moon, it was the same. They had a descent stage with all the fuel and engines for landing, and then a much smaller ascent stage to come back up. There's actually some cool videos from the last few of them where they left a video camera on the surface to take a video of the ascent stage separating and going back up to orbit. So here's back to the South Pole, Tycho crater, zoomed in enough that you can't even see really any ejecta. If I go back over this way, you can see some lines, but then the shadows where all the real detail is. Let's see up here. Turn up the exposure too. Oh yeah, that's pretty good. But yeah, it's still quite a wobbly view. See if I can get any more resolution out of the focus knob. Not much. Well, this is back to that Apollo 15 landing site. They were right in here. Okay, well, in the absence of any more questions in the next minute or so, I am going to end the stream, and then I'll try to take some pictures, and if I do get anything good, I will probably post it on the observatory website. The observatory website needs some attention. I've just finished up my last classes of my PhD, so hopefully I'll have some time to give some attention to that website. I've only slightly adjusted it since I inherited the observatory from the last guy who was in charge of it. Okay, well, thanks everyone for coming. Have a good night.